The next presenter, Pranav Peter.
Good morning. I'm Pranav. I'm coming from Amrita School of Engineering. So I graduated in 2018 from Amrita School of Engineering in Master Technology in Embedded Systems. I'm guided by Dr. Sujati. So my topic of dissertation was Robotic Grasper based on an end-to-end neural architecture using a Raspberry Pi. So I'm combining the latest technologies like deep learning on an embedded platform like Raspberry Pi on a robotic system. So let me set the premise. A traditional or a typical robotic system in terms of grasping, a robotic grasper we call it, or an object manipulation system. So what happens there is you have a robot either like this, moving like this, it's called a SCARA robotic arm, or it will be going like this, which is an articulated robotic arm. So it is fixed at one point and the other end is allowed to move freely. So if we can divide the problem into two parts. One, the object's position is known, but what the characteristics of the object is not known. So there it is basically two tasks, which is pick and place and binning. So there you don't need any kind of intelligence as such, because the position is known. You just need to have an intelligent grasping. That can be a mechanical solution where you can just take the object from a position and put it into another position. So the programming required is just to move from one position to another position. But once you take the assumption out that the position is not fixed, it can be anywhere within the workspace of the robot, then little bit more intelligence is required to recognize the object first and then to grasp it successfully and move it to the required destination. So that is where we are coming in. Our work works on that aspect. So the traditional system has three stages. You have the sensing part and the pre-processing. Then you have the object detection, localization, recognition, that algorithm running on. The third part is the robotic algorithm, that is the robotic programming. So these three are connected in stages. So what we found out was the communication between these stages is where the efficiency of the entire system lacks. So we propose, we hypothesize that what if we can have an end-to-end solution, that is from the sensing to the motor actuation, we have a single architecture doing all the job instead of different stages. So we are proposing a neural network based architecture, and that is running on a single computing platform, that's the Raspberry Pi. So I'm going to just summarize my work first in abstract and then go to details. So first, what we propose is we are using any kind of a robotic system. So here in our work we are using an articulated robotic arm. There we put the camera on the gripper, that is called the grasper gripper, we can call it either way. Traditionally the camera is kept outside the robotic system so that it can observe the entire robot. Here we are observing more of the object. On top of that, we are using the Raspberry Pi to connect the camera as well as the motors. So what we are trying to achieve is give a goal, okay, reach this object and bring it back. So the object's position is not known. On top of that, the robot is not programmed. The robot is not given any input, go to X, Y, Z and go there. Robot, as far as the robot is concerned, the sensing is the camera. So it is told, this is the goal, bring it out and just drop it. That is the experiment we are trying to do. So the technical difficulties we need to address is, first, what is the image resolution we need to set on, because larger resolution will not allow us to do it on a Raspberry Pi because of the limited computing resources. So the step size means how much movement should I do minimum to allow the robot to work precisely. On top of that, how long does it take to reach the goal, and how long does it take to train the system, because this is a learning system. We use reinforcement learning as our framework. So a specific version of reinforcement learning called as Q-learning is used. So how can you reduce that training time, and then how do I isolate the Raspberry Pi from the motor controller? So that we do using an octave isolator, because that is an issue which most people face, wherein you cannot combine it so easily with the Raspberry Pi. So this is the need of the system we need to address. How do you transition from an unknown environment, which is if you don't know the entire area, it can be any background, it can be any height. From that point to how do you go to the goal we need to set. Then how do you set the goal? Is the goal a human defined goal or just always a singular goal? So the goal, because it's a human intervention, we need to reduce the human intervention. How do you do that? Then what is the scenario if you change the goal? So this is my system architecture. So this is where the entire work is summarized. So my Raspberry Pi is my computing platform. I have the input image coming in. So this is a 15 cross 15 pixel image actually. That is my resolution. This is a 2-layer neural network. 2-layer meaning from the input to hidden layers and the output layer. So it is not extremely deep, but it should be considered deep. It is not a single layer one. So we have new technologies being involved in this space. So this is an we developed this concept called as I know and I don't know signals. Along with that, the motor 1, 2, 3 are continuous values given to the motor to tell where it needs to go. Along with that, the reward predictor tells you whether it reached the goal or not. Now, the confidence disruption is used for increasing the learning capability of the system. So I'll explain that in detail. This is all connected to the robotic arm there, so that is our touchable robotic arm. So what happens is transitioning from unknown to the unknown, unknown to the known, occlusions, all can be solved with I2 signals. Then the image resolution, step size, reaching the goal, the effective training time can all be done from going from discrete to continuous. Discrete is what has been done in the previous one. So goal definition, all that can be solved using our method. These are hardware and software requirements. So just to show you the results of our video, the results of our work. So this is the object gets there. So this going near the object, fix it, done. So and just drop the object. So this is the result. So this is how training happens. Can I just conclude?
Yeah.
Conclusion. So what we were able to achieve is that we can use a simple architecture like the Raspberry Pi as a single computing platform, wherein it can have a standalone system going from the camera, which is the sensing capability, to the actuation of all the motors, and it can be done to solve simple tasks. So as you increase the training and the capability of the robot, you can achieve more complex tasks. So this is a published work. We published a paper in AdCom 2018. It was in IEEE related to this work.